This is part 3 of lecture 21 review of the eigenvalues and eigenvector. So we will continue with the rest of examples. So the one with the imaginary eigenvalues. So in this case, the anti-symmetrics or the skew matrix. And the last one is the reverse example. And let's start with the number 5. This is also called the rotational matrix. Let me also put that name here, skew or anti-symmetric. Okay, so the rotational matrix has this form. So let's give it an example. Let's say if I multiply it by 1, and this will give me minus 1, 1, right? So if I have x, y, z here, so if I have this, my initial 1, 1, this 1, 1, and my minus 1, 1 will be minus 1, 1, so I'll be here. So this is, see, I rotate this by some degree here. So it's intuitively what I want to say is that it's clearly impossible in this case to have some real eigenvector, right? Because you want to rotate some vector, so it will not be parallel, it will not be in the same direction as what it was, as this green one. See, because this is rotation, and you will never end up with having blue one the same, like it goes here or parallel to this. Okay, and we will run into a problem with the eigenvalues. So let's see what will happen. So let's continue with this example. We're interested in the determinant of q minus lambda I equals 0. So minus 1, 1, 1, minus 1. And the compute the determinant will be lambda squared plus 1 equals 0. So lambda squared will be minus 1. So lambda 1 will be the imaginary number or the complex form, and this will be minus imaginary number. Okay, see, we end up with some imaginary number, some imaginary or complex eigenvalue here. And what we know is that we know that, well, these two are the conjugate complex of each other, but they are imaginary. And this is also a good chance to see that even if you have a completely real matrix here, these are all real, right? Real matrix. You will end up, there's a possibility that you can end up with the complex eigenvalues. So that's a good point to make here. And also this matrix is also what I mentioned here. This is skew and anti-symmetric. So what does that mean? Is if the q transpose is equal to the minus q. So the transpose of q here is here, and then that's exactly to the minus 1 times the initial value, which is, yep, you get plus 1 here, you get minus 1 here. So just remember that if you stay with the symmetric matrix, you will end up with the real eigenvalues and real eigenvector, but this is the opposite example, the complete opposite of what is symmetric, right? This is anti-symmetric. So if I imagine there's a bar here and the left one being the anti-symmetric, this is the symmetric, and let's call this like symmetry bar or something. So in this case, you end up with a really real one, while this one you end up with imaginary number of eigenvalue. So here in this case, this is completely what we have here, the anti-symmetric case. And when you have again the symmetrics and then like something from here and into the middle of here, you will still have the nice case of a real eigenvalues. So that's about the 5th example. Now I mentioned that this is, well, this end up with the complex eigenvalues, and that's not really as pleasant as what we used to have here, right? In the first 4 example, those with the real one, because they are just really clear and really real. Yeah, I don't even know what I want to say, but that is, it seems really nice when we have that real eigenvalues. But this one is not so nice. But there's also an even worse one, the case when we have only single eigenvalue. So we don't have enough eigenvector, right? So this is an example of, let's say, this matrix. And let's do the drill, right? 3 minus lambda 1 0 3, and then you can multiply this minus 1, and then oops, I should have had this. That's why it gets so confusing. So you have here, so okay, so you have there, it's there. So eigenvalue 1 is 3, eigenvalue 2 is also 3. So when you want to find the eigenvector, you will have to look for this kind of the null space of this matrix, which is any number here, some constant, and 0 of here. And the second eigenvector is also this one. So this is also eigenvector 1, eigenvector 2. So you see here that we can see it like it's not even like a full rank, meaning that we don't have those independent eigenvectors. So x1 is x2. And here it's also a problem. And this is the worst problem, because we're lacking that eigenvector. And this will cause problem later on, because in the later chapter we will create that matrix of eigenvectors. So this is eigenvector 1, eigenvector 2. And if we have the same column, that means this matrix is singular and this is not invertible. And we will see why that in not invertible matrix of eigenvector will cause a problem in the future chapter. So that's it. Thank you.